Okay, do another example. Show how this works. Uh, let's see. Whoops. Okay, example 3. Okay, here we're going to use it. The example, we're going to take this function and just go back to our approach to find the Taylor series. Okay, so which basically means we're going to do the same thing we did before. We're going to find the Taylor polynomials and then the nth Taylor polynomial, basically, which will be a Taylor series then. So you would start off the same way: f prime 1 over x double prime minus 1 over x squared triple prime 2 over x third and fourth derivative minus 6 over x fourth, fifth derivative. That should probably be enough to figure this out. 24 over x to the fifth. And evaluate, we have f of 1 is a 0, f prime of 1 is 1, double prime of 1 is minus 1, triple prime of 1 is a 2, fourth derivative at 1 is negative 6, fifth derivative at 1 is 24. Okay, so you would start off over here then forming that series. We would start with f of 1 and then f prime of 1 x minus 1 over 1 factorial f double prime of 1 and x minus 1 second power of 2 factorial and so forth. Now let's fill in what we have here. We've got a 0 for this one, so that won't change anything. We do have a 1 here, so we'll have a 1 times that x minus 1 over 1, and then minus 1, then x minus 1 squared over 2 factorial plus 2 x minus 1 is 3 over 3 factorial minus 6 x minus 1 to the 4th over 4 factorial. And you can see that continues. We get, put the last term in here, we get 24 x minus 1 to the 5th over 5 factorial. And it continues. We can simplify a little bit here. X minus 1 minus an x minus 1 squared over 2. And this next term, actually, because the 2 drops out, this should just be a 3. And this one, 6 drops out and leaves a 4. And the next one, guess what happens? The 24 drops out and leaves a 5. So I think you can see that the general form here, put it in closed form like so. We've got minus 1 to the n. It's alternating. X minus 1 to the n. And it looks like we just have an n underneath. So there's our series. And we're not going to show that this one converges. Might be a little more work than we bargained for. So again, because that means we have to look at the remainder term and show that that remainder term heads to 0. So that's a problem in itself. We did enough for this one. So what we see is we'll assume that that can be done and that our function is equal to this. And now you could look for radius of convergence if you wanted to for this one. Um, we weren't checking that here, but you could. Again, you'd have to do this. And you'd have that. Be looking at this, and let's see if we simplify this one more step, and you're finding the limit. So this will be simplified as just an x minus 1, and then times this n over n plus 1. Now you can see that this thing does head to just the x minus 1, like so. And if you set that less than 1, that guarantees convergence, which means this, and that x is less than 2, greater than, well, yeah, 1 is 2, and we add 1 is a 0 here. Okay, so now what happens at 0? Well, you can see based on our series, at 0, you would have this. Negative 1 to the n, and you have a negative 1 to the n over n. So that would become negative 1 to the 2n, which is over n, which is a positive 1. So that would be divergent, because that's a harmonic series. At the other point, at 2, we'd have this. Negative 1, and then we'd have a 2 minus 1 inside here, which would mean a 1. So we'd have this. This would actually converge, because it would converge by the alternating series test. You could show that. So we've seen this one enough. It's conditionally convergent, but it does converge. So at 2, we would actually pick up an extra point. So we can conclude then that completely that our interval would look like this. Okay, that's the actual interval for this one. Okay, so